Is this visible?
Yes, sir, it's visible.
All right, great. So today we are going to talk about what is known as the Gram-Schmidt orthogonalization. Okay, so Gram-Schmidt orthogonalization, I have already briefly mentioned to you in my previous class. That is, what if I don't have a set of orthogonal vectors? Okay, if I don't have a set of orthogonal vectors, in that case, we can create our own set of orthogonal vectors given in like any set. So suppose I need a set of 3 orthogonal vectors. So all I can do is but I don't have those 3 orthogonal vectors. So what I can do is I could construct my own set of orthogonal vectors using the set of 3 non-orthogonal vectors. Okay. So basically, it's a process whereby a set of functions that is neither orthogonal nor normalized can be used to construct an orthonormal set that spans the same function space. So let me try to demonstrate this to you using a scenario which you're already familiar with. Okay, so let's take the case of vectors. Okay, ordinary vectors. So let us say I have, now remember the terminology that we use, we are going to use the word orthogonal, right? Okay, the word orthogonal, when you say in the context of vectors, it what should come to your mind is perpendicular. Okay, we don't talk about perpendicular functions, we call them as orthogonal functions. Okay, so basically two functions, if their scalar product is 0, then they're orthogonal. Like just like how two vectors, they're said to be perpendicular if their dot product is 0. So let us say I have two vectors here. So this is one vector. Let me use some other colors. This is one vector, and say this is another vector. Okay, so as you can see here, these two vectors definitely they are not perpendicular to each other, right? So this is one vector, and this is the other vector. So this vector, let's give it some name. Okay, let's call this as vector A0. This is vector A0, and this other vector, let's give it some name. Let's call this as A1, vector A1. And the angle between these two vectors, is theta. Now, these two vectors, they're definitely not orthogonal, right? So A1, so A0 and A1, A0 and A1 are not orthogonal. A0 and A1 are not orthogonal. Okay, so but we can, according to Gram-Schmidt orthogonalization, according to the Gram-Schmidt orthogonalization, okay, we can obtain uh, or rather we should say we can construct another set let's say we call this set as B0 and B1. We can construct another set B0 and B1 which are orthogonal. A0, A1, they are not orthogonal, but we can construct from A0 and A1, we can construct B0 and B1. That is, from A0, we can get B0, and from B1 and A0, from A0 and B1, we will construct, A0 and A1, and from A0 and A1, we can construct this B1. Okay, so all the remaining vectors we can keep on constructing. So now these two will be orthogonal. They will be orthogonal. Okay, so that procedure is known as the Gram-Schmidt orthogonalization. So the idea behind this is very simple. Okay, so you all already know this, right? Any vector, okay, any vector. So suppose, let's say I have a vector like this. Let's say I have a vector. You can always break down this vector into its components, right? So this vector, I could always break it down into its components. So this is one component and this is another component, right? So I can always do that. These are the two components of the two vectors of this one. So this is like the projection of this vector. So this is the projection of this vector in along the horizontal and along the vertical. So now let's say along the horizontal, we have like something like a unit vector. Along the horizontal, we have something like a unit vector. Let me draw it here first. So along both directions, we'll have two unit vectors. One will be unit vector along the vertical, another one will be unit vector along the horizontal. So let's say, let's give some names. Okay, so this unit vector, let's say we call it as u1, unit vector 1, and this is a unit vector u2, unit vector 2. Let us say this is some vector p. Okay, this is some vector p. So this vector p will have a component, okay, and this will have another component like this. So this component that we have, okay, this component that we have, what is this component equal to? That is nothing but magnitude of p times whatever angle it is making. Suppose it makes an angle theta with u1. So what is this component? It is magnitude of p, magnitude of this vector into cos of theta, and this component you already know, this is p sine theta. Okay, this is p sine theta and p cos theta. So now we can write this down. This p, this vector p, we can write this out. We can write this down. Vector p as p. Sorry, we can write this as p cos theta, p cos theta into u1 cap plus p sine theta into u2 cap. You can write it like this. So we might as well call this, okay, this entire part, we might just, because it is magnitude, scale magnitude into unit vector, that is going to give me some vector. So we might as well just call this as this one, this vector p. We could call this as a combination of two vectors. This is one vector. This vector is, let's say, the parallel component. Okay, this is the parallel component, and this other vector, this one, this is this p parallel, this other vector, that is the magnitude and the unit vector together, this is going to be the perpendicular component. So this is p perpendicular, this is p perpendicular. Okay, so now how do you get this p perpendicular, this perpendicular component? How do you get this? You can get it from here. So what is p perpendicular component? P perpendicular component is simply the original vector. The original vector is p minus the parallel component. Is this clear? Just give me a second. Okay, coming back to this. Has everybody understood this? All of you? Is this clear? Is this point clear, everyone?
Yes.
Okay, so what we mean by here is, suppose I want the perpendicular component. Okay, how do I get the perpendicular component? From the original vector, subtract the parallel component. Just subtract the parallel or the horizontal component. When you from the original vector, when you subtract the horizontal component or the parallel component, you'll get the perpendicular component. Now, this perpendicular component, so this parallel component, what do we have here? So here now, this parallel component, there is p parallel, this parallel component. How can we write this? This parallel component is simply p cos theta into u1 cap, right? P cos theta into u1 cap. So over here, this cos theta, how do you get this cos theta? How do you get cos theta? One way by which I can get this cos theta, one way by which I can get this cos theta is if I take the dot product of u1 cap, if I take the dot product of u1 cap, okay, with p, if I take the dot product of u1 cap with p, what will that give me? What will that give me? If I take the dot product of u1 cap with p, what will that give me? Modulus u, modulus p into cos of the angle between them. Modulus of u is, u1 is anyway 1 because it's a unit vector. So what is left behind is modulus p. Modulus p times cos theta. So this gives us this cos theta. Cos theta, it is simply equal to, cos theta is equal to u1 dot p, u1 dot vector p divided by the modulus of vector p. Okay, or rather actually we don't need to do it like this. We can just leave it as it is. We'll just leave it like this. Okay. So dot product of a unit vector with a vector will give us the projection of that vector. Okay. So this is important. So now keep this idea in mind. Okay. Keep this idea in mind and let's go back here. So we have here a1. Now what do we want to do? We want a vector which is perpendicular to a0. First of all, we need to normalize a0. First of all, we need. And what do you mean by normalizing a vector? Normalizing a vector is simply finding the unit vector. That's all. Because after all, how do you normalize something? You just take that vector, divide by its magnitude. That's the whole purpose of normalization. So when you take a vector and divide by its magnitude, you're getting the unit vector. So that is basically your normalized vector. Okay, so now let's normalize this a naught. Okay, so first what we do is, first step is normalize a0. So how do you normalize a0? All you need to do is take vector a0, and divide it by its own magnitude. Take vector a0 and divide it by its own magnitude. Okay, this is the normalized vector. So let's call it as n0 cap. This is a normalized vector, so it will be somewhere over here. So this is your n0 cap. Understood? So this is just like your u1. Okay, this is just like your u1 cap. Okay, so now there is a better way to write this. Okay, there is a much more generic way to write this. And what is the generic way? The more generic way to write this is a0. I could divide this. What is modulus of a0? Modulus of a0 you can simply find out by taking the dot product of a0 with itself. You take the dot product of a0 with itself, and then this is going to give us dimensions will be square, so you have to take the root over of this, so to the power half. Okay, so this is what we have. Understood, everyone? Now let's generalize this even further. Okay, let's generalize this even further, because dot product that we have over here, this dot product is for vectors, no? But in general, we have the scalar product for any vector space. So in general, how can you write down this n0? N0 can be simply written as a0, that is a normalized unit vector. It is a0 divided by what is a dot a0 dot a0? This is nothing but the scalar product of a0 with itself. This is the scalar product of a0 with itself. Is this clear, everyone? Let's call this equation number 1. So we have got n0. Okay, we have got this unit vector n0. Is this clear, everybody? Are you with me? Yes or no?
Yes, sir.
Okay.
Yes, sir.
All right. So now once we have got this unit vector along this, now we'll proceed to find out a vector which is perpendicular to n0. In other words, we are looking for a vector which is perpendicular to n0, that is in this direction. We are looking for a vector in this direction which is perpendicular to n0. Okay, this direction. In short, what we are looking for is the perpendicular component. We are looking for the perpendicular component of a1. Okay, we are looking for the perpendicular component of a1. This is the vector that we want. This is a perpendicular component of a1. So this perpendicular component of a1, let's call it as b1, just to keep things more systematic. So we'll call it as b1. So what is b1? Next, obtain the perpendicular component of a1. Obtain the perpendicular component of a1, that is b1. That's what we are trying to obtain here. So this b1 is what we want. And what is this b1? b1 is a1 perpendicular. b1 is a1 perpendicular. Now how do you get a1 perpendicular? How do you get the perpendicular component? How do you get the perpendicular component? You get the perpendicular component by taking the original vector and subtracting the parallel component. So this we get by taking the original vector. The original vector is a1. The original vector is a1. I'm using this formula. The original vector is a1. From there, I'm subtracting the parallel component of a1. I'm subtracting the parallel component of a1. Now, what is the parallel component? Parallel component is p cos theta into u1 cap. P cos theta into u1 cap. P cos theta, right? P cos theta. What is p cos theta? P cos theta is u1 cap dot p. Okay. So this will be equal to, so we have a1, okay, minus, so we have this parallel component is equal to p cos theta into u1. So p cos theta we want to find out. P cos theta is nothing but u1 cap into p, which is, what is u1 here? What is u1? u1 is n naught, right? The unit vector. u1 is a unit vector. In this case, u1 is nothing but n naught. So this is equal to n naught cap. Okay, and you have to take the dot product. You have to dot product with p, that is the original vector. Which is the original vector? The original vector is a1. The original vector is a1. Okay, the original vector is a1. n naught cap dot a1. Okay, so this is going to be your p cos theta, and what is, and into times u1. So what is u1 again? u1 is your n naught times n naught cap. Okay, now let's write this. So this gives us b1 is equal to, so b1 is equal to a1. b1 is equal to a1 minus, what is this one? This is nothing but your scalar product of n naught cap with a1. Scalar product of n naught cap with a1. Sorry, this is a vector times n naught cap. Okay, so this will give us, this basically you're trying to find out the projection of one quantity. So essentially you're trying to find out the projection of this along this one. So P will have horizontal and vertical components. So this is your horizontal component. Okay, and this is your vertical component. We are only interested in the horizontal component. That is the component of P along U1. Another way of looking at it is P cos theta, which is nothing but this scalar product. This is the component of P along U1. Okay, so we already know we can write this P. We can write this P in this way. So this vector P, remember, vector P can be written as something into U1, right? Something into U1 cap plus something else into U2 cap, right? We can write this vector P like this. So let's say this is some coefficient. Okay, this is some coefficient. Let's say a1, and this is some coefficient a2. So we can write vector p like this, right? Some coefficient into u1 plus some coefficient into u2. Yes or no? Can we do that, right? We can do that. Yes or no? We can do that, no? This is generally how we write a vector. Unit vector into coefficient. So now you can see here, that is, P is a linear combination. P is a linear combination of the basis. Which basis? The basis is u1 cap, u2 cap. P is a linear combination of this basis, this one into this one. So this you can consider it to be like if you have a function. So function is you have the basis multiplied with some coefficients like this. So how do you get these coefficients? All you need to do is just take the dot product of this basis, that is u1 dot product with p, that is going to give a1. If I want a2, what do I do? U2 dot product with p. So that's what it's going to give me. So this is basically a number. Okay, so this is basically a number that we have over here. So this gives us b1 is equal to a1 minus, this is going to give me the coefficient of expansion. If you try to expand a1 in terms of n naught, okay, and whatever is the other vector, so this is going to give us, let's say, a0 comma 1. Okay, we'll just call this coefficient as a0 comma 1. Okay, this one comes from here just to distinguish, times n naught. Okay, times n naught. So this is the vector b1. This is this vector v1, the perpendicular vector v1. So now check if b1, third step is just verify that n naught cap. We'll have to verify, because what we have done, is it correct or wrong? We have to verify that n naught cap is perpendicular to b1. We have to verify this, n naught cap is perpendicular to b1. So how do you verify this? How do you verify whether something is perpendicular or not? How do you verify? Just take the dot product, that's all. So you take the dot product of n naught cap with b1. Okay, so you take the dot product of n naught cap with b1. So this is equal to n naught cap dot b1 is a1 minus a0 comma 1 n naught cap, and over here n naught cap, this is nothing but the scalar product of n naught cap with a1 minus, this is a constant, so it will come outside, a0 comma 1, and then we have scalar product of n naught cap with itself. This is a self dot product. This will anyway be equal to 1. This is anyway going to be equal to 1. And this we already know, right? n naught a1 we have already written as a0 1. So this is going to give us the first term is going to give us a0 1 minus, this is also a0 comma 1, and this is going to be equal to 0. So n naught is perpendicular to b1. As expected, n naught is perpendicular to b1. So now we want the other vector. We want this vector. We want a normalized vector, right? That is, we want n1. We want n1 cap. So how do you get n1 cap? Just normalize. Next step is normalize b1 to obtain n1 cap. That is, n1 cap is simply equal to b1 divided by the scalar product of b1 with itself. Scalar product of b1 with itself to the power 1 by 2. So that is your n1. So from there you have it. Okay, so from a0 a1 we got b0 b1, these are orthogonal, and from b0 and b1, okay, we already had n0 is a unit vector. from there we got, by normalizing b1 we got n1. So that means, so therefore n0 and n1, n0 and n1 is an orthonormal set. Understood? So we started, where did we start with? We started with A0 and A1. Okay. We started with A0 and A1. And from A0, we got N0, and A1, we got rid of that, parallel projection. Okay. From A1, we subtracted the parallel projection. From A1, we subtracted the, here it is, A1, we subtracted the parallel projection. Once we got rid of the parallel projection, the perpendicular projection is left behind. That perpendicular projection, this is the formula. This is how you get the perpendicular projection. And this perpendicular projection, you normalize it, that gives us the unit vector. That is the this is the normalized vector along this b1. So n0 and a1, that is going to be the set of orthonormal, and this is going to be the set of orthonormal set. Okay, this is the orthonormal set that we're looking for. Okay, now suppose we want one more vector. Okay, let's say we want one more vector like this, which we want it to be perpendicular to both n0. We want that vector to be perpendicular to both n0 and a1. But let's say we have another vector like this. Okay, let's say we have some vector like this, which is not perpendicular to both n0 and a1, n1. So let's say we have one more vector. That vector, let's say call it a0, a1. Let's say this vector we call it as a2. This vector we call it as, let's say, a2. Then how do we obtain a vector which is from a2? We want to obtain a vector like this. We want to obtain a normalized vector like this. We want to obtain a normalized vector. That normalized vector we call it as n2 cap. Okay, and this normalized vector should be, it should be perpendicular to both n1 as well as n0. It should be perpendicular to both n1 and n0. Then n0, n1 and n2, they will form an orthonormal set. So how do you get this n2 from a2? Very simple. Just have to, generalize this. A1, from a1, how did we get n1? From a1 we subtracted the parallel component. In the same way, from a2 you subtract the parallel component. So how do you get rid of the parallel component from a2? So what we do is, next, okay, so from A2, remove the parallel components, from A2. That is, by removing these parallel components, we will get some other vector. That other vector, let's call it as b2. By removing the parallel components, we'll get some vector. That vector we'll call it as b2. So from a2 we'll get b2. So how do you get b2? Just generalize this step. Just like how we got from b1 from a1. Similarly, you will get b2 from a2. So we'll get b2 from a2. So how do you get it from a2? Just remove the parallel component. The parallel component that A2 has with this one, N0, and the parallel component that A2 has with N1. Just remove the parallel components. Just generalize this. So first parallel component with this one. So we'll have minus A 1 2 and 1 cap. This is the parallel component with respect to n1, and then you have to subtract the parallel component with respect to n2. So a 0 to n0 cap. Okay, I have just generalized this one. So that gives us b2, and once we get this b2, so from here, very simple, normalize b2 to obtain N2. Normalize B2 to obtain N2. That is N2, just like before, N2 cap is simply, it is equal to, N2 cap is equal to B2 divided by just like that. Okay, so that's how we build upon this one. Okay, so first you get N0, and from there, using this N0 and A1, you can obtain B1. Normalize this, you get N1. Then from there, from these two, N0 and N1, you obtain, and this you subtract these two components with A2, you get B2, and then normalize this. So with that, we will get this one. So now we are orthonormal set. Okay, N0, N1, and N2. N0, N1, and N2. This is going to be an orthonormal set. N0, N1, and N2. This will be our orthonormal set. So that's the whole procedure behind your Gram-Schmidt orthogonalization. Now here I have used vectors. I have used vectors to explain this, but in general we'll have to use functions. Okay, that's what is there in the slides. Okay, so when you go to the slides, you'll find that we have functions over here. So this I can just go through this. So this is called a sequential autonormalization. You create the first orthonormal function, just like phi naught. Phi naught is like your n naught. Okay? So here, what we have written as phi naught. Okay, phi naught. This is same as in our example, that n naught. Phi naught is just like your n naught. Okay. Then you have in our example we had used from A. This vector A's were there. Okay, these vector A, and from these vector A you go to vector B, right? Vector B's, and from there we go till the vector N's, right? So over here we start with a set of vectors. So let's say A's. These are your, I think, the functions, chi functions. Instead of vector A, we'll have like the chi functions. From there, we'll go to psi, and finally we'll reach the orthonormal set, which is phi. Okay, so that's how we get this. That's how we get this. This is the steps. Okay, so you get this phi naught, that is the orthonormalized, the normalized, the first one. Phi naught, you get it directly from chi naught. Okay, because n naught we get it from a naught, right? N naught we get it from a naught. So similarly, phi naught you get it from chi naught. Okay, so get the first orthonormal function phi naught from chi naught. Next phi 1 from chi 1, and so on. So that is known as sequential autonormalization. So this is how we have same thing. How did we obtain this? Just like this. Just like the same way we obtained n naught. So how did we obtain n naught? We obtained n naught like this. N naught we obtained from a0, right? N naught we obtained from a0. So similarly, phi naught we obtain from chi 0. Chi 0 is our starting set of vectors. Then once we do this, then construct an intermediate function psi 1. Okay, so which is the psi 1? Which is the psi 1? Psi 1 is your b1. Psi 1 is your b1. B1 is, what is b1? B1 is a1 minus a naught, n naught. Okay, so we could just actually do this over here. Let me just get this here. A, B, N, okay, chi, psi, and phi. Okay, A, B, N, chi, psi, and phi. Let me just try to do this over here. From vector A, we go to vectors B, and from vectors B, we go to vector unit vector N, and here this was the chi. From chi, we go to psi, and from psi, we go to finally the normalized one. Okay, the orthonormal set. Okay, let's just try this over here. So what do you do first? N naught you get it from a naught. Okay, n naught you get it from a naught. So let me try to write down the expression here. So instead of n naught, instead of n naught we'll use, we'll replace it with phi naught. So n naught, here we had n naught, so instead of n naught we'll use phi naught. So what is phi naught equal to? Phi naught we get it from a naught, and a will get replace it with chi. So we have, instead of a we'll have chi naught divided by the scalar product of chi naught with itself to the power 1 by 2. This is what we get. Okay, this expression, equation number 1. Now this intermediate function. Okay, let's get this intermediate function. So what do you want next? We want b1, right? Next, what did we get here? We got b1. So let me just write this b1, making the same translation. So we have b1, and instead of b1 we'll use psi. Instead of b1 we'll use psi1. Okay, b1 instead of b1 psi1. This is equal to a1. Instead of a I'm using chi. Okay, instead of a I'm using chi, so chi1 minus a01. We'll leave it as it is because they're just constants. A01, and then we have n0. What is n0? N0 is, right, n0 is nothing but phi naught. Okay, so this is what we have. So then after you have got this b1, then you can normalize. You normalize b1 to obtain n1. Okay, you normalize b1 to obtain n1. So this is over here. So you obtain n1. N1 means, n means phi, and it will get replaced with phi. So instead of n1 we'll get phi1. And what is phi1 equal to? Phi1 is equal to b1. B1 is nothing but your psi1 divided by psi1 to the power 1 by 2. That's that. Okay, so this expression, this is equation number 2, and then this is equation number 3. Okay, same thing. In case you get stuck in the exam, you can just use this. You can just use this kind of a translation. Remember, this example is easy to remember. This example that I have given here, it's easy because this is vector, you already know. So you just do this translation and you will know what is the Gram-Schmidt orthogonalization process. And then next, another intermediate function. Okay, so this one we have, right? So let's construct this one, that is psi2. We want to construct psi2. So how do you get psi2? Psi2 we can get it from here, psi2, because b2, right? Psi will replace, b will replace with psi. So this equation b2 instead of b2 we'll write psi2. This is equal to a2. What is a2? A2 will replace it with chi2 minus a12 and n1. And what do you write n1 as? We write, instead of n1 we write phi1, and then the last one is minus a02, a0 comma 2, n0. Instead of n0 we will write phi 0. You can see here it's the same expression. The same expression. Is that clear, everyone? Everyone understood? This is your Gram-Schmidt orthogonalization. All right, everyone? Is this clear?
Yes.
Any questions? Do you have any question? Okay. So this is straightforward, right? So in general, given the prior information of this phi n, the next orthonormal function is formed by the following two steps. That is, this is that, removing the projections, removing the parallel projections. This is the summation of all the parallel projections that you have got so far. Okay, so you can sequentially, you can keep on constructing your orthonormal basis. Okay. All right, so that's your Gram-Schmidt orthogonalization. So this is a problem which is a little bit involved. It will take a little bit of time. So I'll do this problem at a later time. Let's do this problem. Okay, the problem is a set of functions is orthonormal on this range. Okay, on this range, that is 0 to pi. This set of functions is orthonormal, and this set of functions are given in this way: phi n of x is equal to under root 2 minus delta n0. So this is the Kronecker delta function. cos nx, where n equal to 0, 1, 2, 3, and so on. So this delta n0, it will take the value 1. It will take the value 1 only if n equal to 0. For all other values of n, for n equal to 1, 2, 3, 4, and so on, this is going to be 0. Okay. So we need to expand. We need to expand these functions, this function f and this function g. This is what we need to expand in terms of these 5 n's. Okay. So that's what we need to do. And then, of course, once we have expanded this, then we can obtain the scalar product. Okay, we can obtain the scalar product. I think I did this already, right? I did this already, this problem. I guess I did, because I remember doing this. Does anybody remember me doing this problem? Yes, we did this already. Yes. So I think I'm done with these set of slides. If you have any questions, you may ask me. These set of slides, I'm done. Next we have this linear operators. Okay, next we have linear operators. So before we proceed to linear operators, if you have any questions, you may ask me now. Anybody? Okay, so next class we'll do this Legler polynomials, that problem. Okay, we'll do it at a later time. Now let's proceed with your linear operators. Okay, I just have maybe 10 minutes more. So I'll proceed with this and then I'll take another class. Then we'll try to finish this linear operators. Okay. Okay, so what is an operator? An operator is a mapping. It's a mapping between functions in its domain and functions in its range. So that's the definition of an operator, because an operator operates on a function and it produces some other function. So we have functions in the domain and functions in the range. So this mapping between these two, this domain and the range, the function in the domain and the function in the range, this mapping is known as an operator. So here, our discussion that follows here, we will consider only those operators whose domain and range are both in all or part of the same Hilbert space. By the way, do you remember what's a Hilbert space? What's a Hilbert space? Who can tell me? What is a Hilbert space?
A vector space wherein the coordinates are functions, complex functions.
No, that's not a Hilbert space. Hilbert space is a vector space, correct. Then, under what condition?
So scalar product is defined.
Very good. Okay. So a vector space in which the scalar product is defined. So that is known as a Hilbert space. So we will consider only those operators whose domain and range are both in all or part of the same Hilbert space. So both domain and range, they are subsets of the same Hilbert space. So those kind of operators is what we'll be looking at. Okay. So linear operator, a linear operator A, okay, we represent it like this, boldface A, on some vector space V is a map that carries each vector X in which belongs to V to another vector which belongs to the same vector space. So in essence, so suppose I have some vector space, oops. So let's say I have some vector space. This is my vector space V. And then over here, I have some vector X. Okay. Then suppose from this vector X, if I am able to go to some other vector, from this vector, let's say I'm able to go to some other vector in the same vector space, to some other vector which we call as y, which lies in the same vector space, then this mapping which takes me from this vector to this vector, this mapping is what we call as the operator. So this is the operator which takes me from one vector to another vector. So that's a linear operator. Okay, and then we write, because I'm getting y from x, right? How do you get y? We get y when you apply on x, you apply this a. So we write it like this. So we say that A is an operator. A operates on a vector x and it gives a vector y. And this vector y and x, both of them, they lie in the same Hilbert space, in the same vector space. Okay. So let's say I'm having any two vectors x and y, which belongs to the vector space, and alpha and beta. These are two numbers, these are two real numbers. Then and I have, let's say, any two linear operators. So remember, operators are defined on a vector space. Okay, operators are always defined on a vector space. So I'm having three things here. First is I have a couple of vectors which lie in the vector space. I have a couple of numbers, a couple of real numbers, and I have a couple of linear operators which is defined on the same vector space. Okay, so if that's the case, then a, the vector in the operator a, when it operates on this linear combination of x and y, okay, the operator a, when it operates on this linear combination of x and y, that is the same as the linear combination of a operating on the vectors first. Okay, so it really does not. So what this equation means is it really does not matter whether you construct the linear combination first and then apply the vector, or first you apply the vector and then you construct the linear combination. It does not matter. Again, both will be just the same. So that's a property of a linear operator. Next, another property is, suppose I have two linear operators which are defined on a vector v. Then suppose I construct a linear combination of not the vectors. Remember, this is a linear combination of vectors, but this is a linear combination of operators. So suppose I do a linear combination of the operators, and this linear combination I operate it on a vector. Then in this case also the result will be just the same. So it will become a linear combination of the operators acting on the vector. Okay, linear combination of the operators individually acting on the vector. Next one is, suppose I have two operators. Okay, so I want to apply these two operators on some vector. Okay, so it really does not matter in what order that I operate or them. First I operate B and then I operate A, or then I first multiply these two operators A and B, and then I apply the composite operator. If I apply this on the vector X, in both the cases the result will be exactly the same. Okay. Operator multiplication is associative. Okay, so it does not, I'm having, let's say, three operators A, B, and C. It really does not matter whether you multiply B and C first or A and B first, or you cannot do A and C, because the order has to be maintained as long as the order remains the same, the order in which the operators operate. So here first operator C operates, then operator B, and then operator A. As long as you maintain this order, it really does not matter whether you first multiply B and C or first you multiply A and B. It does not matter. So operator multiplication is associative. Then identity operator. Okay, there is a special operator called as the identity operator. So identity operator is an operator which belongs to every vector space. So every vector space should have an identity operator. So it's an operator which leaves the functions unchanged. So if you apply the identity operator on a vector, it remains the same. So essentially, this is what we're talking about. So identity operator, either you write it as I or you write it as 1. So 1 when you apply on a vector, okay, 1 when you apply this identity operator, when you apply on a vector, the result will be the vector itself. Okay, so that is a identity operator. Then there's something called as an inverse operator. Inverse operator is, suppose I have an operator, okay, let's say, so I have, let's say, a vector space. I have a vector space V. Okay, I have a vector space V. And let's say on this vector space, let's say an operator A is defined. Oops. On this vector space, let us say I define on this vector space, let us say I define an operator A. Okay, then on the same vector space, there will be another operator which we call as A inverse. On the same vector space, there will be another operator which we call as A inverse, such that when I multiply these two operators, okay, when I multiply these two operators, either A inverse or A inverse A, combination, the multiplicative combination of these two operators, the multiplicative combination of these two operators it will give me the identity operator. Combine these two, that will give me the identity operator. Okay, so example of this one, an example of this is A, it could be your dy dx. Then what will be A inverse? This is an operator, no? So here is what you'll put the function here. So which is, what will be the inverse of d by dx? What will be the inverse of d by dx? A is an operator. The operator A is defined as the derivative. Operator A is defined as the derivative. Then what will be the operator inverse A inverse? What will this be? This will be nothing but the integral, right? This will be nothing but the integral. Okay, this is an example. So when you combine A and A inverse, you will get the identity, because differentiation integration, they will cancel each other out. Likewise, you could have something like this. A equals ln of something, right? Then what will be the inverse operation? What will be the inverse operator?
It's
What will be
exponential.
the, yes, e to the power something. So that means over here, if I do A inverse, A inverse, of course, you have to apply this on some x, right? You have to apply this on x. What will this be? This will be equal to, first you apply, this one, the rightmost one. First to apply A inverse, that is e to the power x, and this one you take the ln, which is nothing but x. So which can be written as 1 into x. Okay, so A inverse is 1. Okay, so that's known as the inverse operator. So inverse operator is that operator which, when you combine with some given operator, it gives us the identity operator. Then there's something called as an adjoint operator. Okay, so suppose I'm having two functions f and g which belongs to a Hilbert space, then an operator A will have something called as an adjoint. Okay, such that when applied to the left member of the scalar product. So this is how you define the adjoint operator. Okay, any operator will have, if it has an adjoint, the adjoint, this is what it means. When you apply that operator to the left member of the scalar product, it will be the same as applying the original operator on the right member of the same scalar product. Okay, so this is the meaning of the adjoint. Okay, so if I have, let's say, some operator A, then corresponding to this operator A, there could be another operator called as A dagger, which is known as the adjoint operator of A. And how do you define this? You take a scalar product, and in the scalar product, you operate this adjoint onto the left member, that is whichever gets conjugated. Left member means f is a left member. That means in the definition of the scalar product, f is getting, you have to take the conjugate of f. So whichever function is getting conjugated, to that you apply that adjoint operator. That is the same as taking the original operator and operating on the right member, that is the function which does not get conjugated. Okay, then operator is said to be self-adjoint. Self-adjoint operators, we are very much interested in self-adjoint operators. They're also known as Hermitian operators. So operator is said to be self-adjoint or Hermitian if the adjoint is same as the operator itself. So which means if I have a scalar product, that is f and g, if I have a scalar product, and let's say I have a Hermitian operator, that means whether I apply A on the left member or I apply A on the right member, in both the cases, it will be exactly the same. So those operators where you can take the operator either on the left member or the right member, leaving the result to be just the same as before. So such an operator is known as an Hermitian operator. Clear? And another one is an anti-Hermitian operator. Okay, an operator is said to be anti-Hermitian if the adjoint is nothing but A inverse itself. Okay, so this is Hermitian. Okay, let me write this down here. This is for Hermitian operator. This is for Hermitian. Hermitian operator A. And if you have an anti-Hermitian operator, if I have an anti-Hermitian operator, this means if I apply A on the left member, this will be the same as applying A on the right member, but with a minus sign. Okay, so that is an anti-Hermitian operator. And finally, we have something called as a unitary operator. An operator is said to be unitary if its adjoint is the same as its inverse, if adjoint and inverse are the same. If the operator has got the same adjoint, its inverse itself is the adjoint. So that kind of an operator is known as a unitary operator. Is that clear? Is this clear to everyone? Okay, so I think this will be a good place to stop. It's 2 o'clock. I'll not take any more. The next class I'll inform you. Okay, I'll inform you on Google Classroom. So if you have any questions, you can ask me now. Else we can stop.